This job, keeping that mud just exactly right, is one of the trickiest jobs in drilling for oil. This guy, the mud engineer, is like a doctor trying to diagnose a man with several illnesses and keep him alive at the same time. You make a mistake, or he makes a mistake, and the driller is going to be trying to pump this mess down the hole. You know, you can lose a hole because of a foul-up like this, when the mud gets so thick it won't pump. And it doesn't take a lot to get it there. That's why your job is so important, and that's why that mud engineer depends on you so much, because you're his right-hand man. The decisions he makes, you will generally carry out. So you've got to do it right, and you've got to do it well. In this program, we're going to learn what water-based mud really is and why the mud engineer has so much trouble with it. Then, we're going to look at what the solutions are for the different maladies mud faces. In Part 3, we'll take a look at how to keep track of what's happening downhole through tests. Then, in the last part, just to make sure you've got it right, we're going to mix a little mud and mix a little caustic. It's got to be done right, or you might lose the hole or your eyesight. Keep one thing in mind. We're not trying to make a mud engineer out of you, so don't ever go second-guessing your mud engineer. What we're trying to do here is give you a little better understanding about what's going on so that you'll know what the mud engineer is looking for. That way, you'll be able to help him better. And as you work your way up to driller, you'll understand a little better exactly what the mud should be doing for you. The first thing we'll look at is an additive called bentonite.
Bentonite is our most common type of mud additive, and it's mixed with fresh water to make a freshwater mud.
Remember all of the characteristics in Part 1 we were looking for? Fluid enough to scour the bottom of the hole, thick enough to carry the cuttings to the surface, good fluid loss control characteristics, and the ability to turn from a liquid to a gel and back again easily.
Well, bentonite in fresh water does all of these things. It makes a good all-around mud. It's just unfortunate that some of the things that we drill up just doesn't agree with bentonite, like gyp stringers, salt stringers, and even the cement used to set pipe. What happens here is a chemical reaction and causes these bentonite structures to get together and act like little sponges, absorbing all the free water that's available and creating a mess like this.
Whenever anybody talks about the mud flocculating, this is what they mean. Usually not this bad. You'd never get this mess pumped up out of the hole.
But there are varying degrees in flocculation that indicate that there is a problem. It is these changes in viscosity is why you take measurements of the mud. It is most important that we keep ahead of the mud system.
And another thing about the mud that's important, mud weight. Now, bentonite isn't really too good at adding weight to your mud. In fact, it only really gives you a weight of about 8.6 pounds per gallon. So you'll probably be asked to mix an additive known as bayrite to the mixture, as more weight is needed.
Bayrite is used to increase the density of the mud up to approximately 22 pounds per gallon. It's inert, it has no adverse effects on chemicals or any other products that you would add to the mud system. You may be possibly asked to add hematite to the system. It too is a weighting agent and has no adverse effects on the mud system or products used within it. It'll get the density of the mud up to approximately 25 pounds per gallon. So you start out with bentonite as your basic mud additive, and then utilize either bayrite or hematite to get the density of the mud to whatever requirements are necessary.
So, you start out with bentonite and add bayrite or hematite to make it heavier. Another problem the mud engineer might encounter: if the driller hits a formation that leaks too much for the normal filter caking features to handle, he might have to add some lost circulation materials to the mud, like ground-up walnut shells, ground mica, and even cellophane flakes. There are a whole lot of additives to help improve or control the natural features of bentonite. Too bad it's not just that simple, though. You know, everything that the driller drills up is a contaminant to the mud system. Most of the solids that he gets into are taken out by your solids control equipment. But when the cuttings start having an effect on the chemical properties of the mud, other things have to be done.
We've already talked a little bit about salts and how they contaminate the mud system. We've also talked about sodium calcium, magnesium, cement that's used to cement casing, and for solving some hole problems, and even some gases that are encountered during the drilling procedure. For all in all, for any one of these particular contaminants that we encounter during the drilling process, there is a specific product that can be used to help control or minimize their effects.
One thing to keep in mind, though, the more additives you put in your mud, the more expensive it's going to get. It's not uncommon to have $500,000 tied up in the mud system and additives alone. So the one thing we definitely want to do is keep it as simple as we can. We're going to get into these additives in more detail in a little while. But let's take a look at one particular contaminant right now, and that's soluble salts. When we talk about these salts, we can be talking about anything from calcium salts to regular sodium chloride, table salt. When bentonite and salt minerals mix, a chemical reaction takes place.
Bentonite and salt just don't mix. As a matter of fact, when they do mix, we have some strange things occur and we lose two of the properties that we discussed earlier. The first being we lose control of viscosity. The second, we lose fluid loss control. When we lose fluid loss control, we find that the filter cake formed is a mushy, not too consistent type mass of solids. It is not conducive to the controlling of fluid loss. As a matter of fact, it tends to increase the fluid loss, and we lose more fluid to the formation than we really want to.
Instead of a thin, hard coating along the wall of the hole like it usually makes, you'll have a thick, mushy, muddy coating. It really doesn't do much to stop the flow of fluids into the formation. This creates several problems. First, you're losing valuable mud that's got to be replaced. Second, you're contaminating the formation, which could jeopardize your hole or a valuable producing zone. And third, you're creating an environment for differential sticking. We haven't talked about differential sticking much yet, but it's a serious problem. It's caused by differential pressure, or the difference between the hydrostatic pressure of the mud and the formation pressure. Just as an example, we'll say we've got 5,000 psi here and 4,500 psi of formation pressure. This 500 psi overbalance causes the mud to want to migrate into the formation, and if the formation has permeability and porosity, if it leaks, an excessive wall cake will build up. Now you're pretty much okay as long as the pipe is turning. It'll wobble and flop from side to side inside the hole, but as soon as you stop for a connection, it's going to settle down into that filter cake. The drill collars are going to be what gives you a problem because they'll lay flat against that wall, top to bottom. The tool joints on a drill pipe will tend to hold the body of the pipe away. So now we've got 5,000 psi pushing against all of the collars except this area where it's in contact with the filter cake. Here we've only got 4,500 psi. Now we're stuck. And the longer we stay stuck, the more the filter cake will build up in this area. Just a minute ago, we only had a small part of the pipe stuck against the wall. Now we've got almost half of the pipe stuck. Let's look at it mathematically. If you have a 10-foot section of drill collars setting up against a differential zone, and 2 inches of the pipe are involved, you've got 240 inches of surface area stuck. If the differential is 500 psi, it'll take 120,000 pounds of force to break it loose. If you wait until 3 inches are involved, it'll take 180,000 pounds of force. It's possible that the string will get so stuck that you can't break it free, and the hole will have to be abandoned.
So all of these problems can be blamed on soluble salt. Well, how do we cure it? Well, the solution is simply to add the necessary chemicals to bring the mud qualities back to the desired levels that we want them. Let's take, for example, viscosity. Contamination of the mud system through soluble salts or magnesium will increase the viscosity of the mud higher than what we want it to be. By the additions of dispersants, which react on the clay particles of the mud system, will tend to bring them down to the levels which we want them to be, or the levels that are required for that particular mud system, density and carrying capacity, and so forth. Let's watch this.
The first problem, too much viscosity, can be corrected with a couple of different chemicals. They're called dispersants. This bentonite has been contaminated with lime. We'll add a certain amount of a dispersant called chrome lignosulfonate. As it's mixed in, it causes the bentonite particles to release the water they've soaked up, sort of like wringing the water out of a sponge. Now the water is free and suspending the mud particles again. This and most of the other freshwater dispersants cause the chemical reaction that reverses the action of the contaminants.
Sometimes when there's a presence of soluble salts in freshwater systems, bentonite just doesn't act the way we want it to. See, the presence of soluble salts tends to reduce the hydrational capabilities of bentonite. So what may happen is we'll add more bentonite than actually required to get the viscosity we want. So what do? The mud engineer may ask you at some point in time to add a few sacks of lime or sodium bicarbonate or soda ash to the makeup water, which will precipitate out any of the insoluble contaminants. In doing that, it prepares the water so that when you add the bentonite, you'll get the viscosity that you want.
Now, these treatments can be used in freshwater muds up to a certain point. If too much of the contaminant gets into the system, nothing can be done for it except to change to another type of mud.
One of your alternatives would possibly be that of attapulgite. Attapulgite, unlike bentonite, does not hydrate in fresh water. It does give us viscosity, and it does give us the type of viscosity that's required in these particular contaminated muds. However, it does not give us fluid loss control. So here we have a product, attapulgite, that gives viscosity like bentonite, but does not give fluid loss control. So how do we attain fluid loss control? Well, by the use of alternative products that are useful in these types of contaminated waters, we can attain both viscosity and fluid loss control. Some of the additional additives that you might look at are your starches, your CMC products, or carbolymethylcellulose as you might commonly know them, or possibly cepiolite in some cases that it may be available to you. These alternative products will add viscosity and fluid loss control where bentonite cannot be used.
Another additive that's needed sometimes to help maintain the saltwater muds is a preservative, because some of the additives like starch will ferment without them. And sometimes defoamants like aluminum stearate or diesel oil are used because saltwater has a tendency to foam up, like you see on waves in the ocean.
When you're drilling through salt domes, mixing a saturated salt mud will tend to alleviate the problems of erosion. Saturated salt muds are such that when you drill through these salt domes, the fluid is so saturated with salt that it will not dissolve any of the salt that you're drilling through. Therefore, problems such as erosion of the wellbore will be minimized due to this characteristic. pH is another concern. Dealing with pH control in mud systems requires the use of caustic soda, a very dangerous chemical to handle. So normally when pH is needed in various mud systems and caustic is added, it is normally added through a chemical barrel very, very slowly into the system. The reason being is that not only will caustic hurt yourself, but it will also contaminate and flocculate a mud system if added too fast. So care in both handling caustic and care in placing in the mud system is of utmost importance.
There's a whole array of additives manufactured by the various vendors. We found this pocket guide for mud technology to be a really excellent study guide for you to use. It's printed by IMCO Services, one of the major mud suppliers. Special arrangements have been made with IMCO to get copies for our people. Ask your driller or tool pusher. It's really a great little book. And it's got a table in the back that'll give you the names and a cross-reference for all of the additives you'll be using and who manufactures them. Well, that's a good start for you on some of the characteristics of the mud. In the next programs, you'll see how you test the mud, as well as some of the tests the mud engineer performs. And finally, how to safely mix the mud.